Hello, my name is Akin Zong, and this is my Comp 3132 Assignment 2. So to start off, we're going to upload our Iris CSV file, as well as import our required modules. Then we're going to read the file and take a look at the first 5 rows. We're going to change the strings in the species column into integers. So of 0, 1, and 2 for the 3 species. So we can see that the species are now numbers. And we're going to split these up into features, these 4, as well as labels for species. We're going to split these up into the train test split. So 20% of the samples, or 30 out of 150, will be used for testing. And the other 120, or 80%, will be used for training. After that, we're going to use our one hot encoded labels, because the 0, 1, and 2 we used for species have no inherent value. One is not better than the other. So we're going to use the getDummies function, and we can see that every species, or every row, which represents one flower, belongs to one species. So for the other 2 species that it does not belong to, it will have a false entry there. And for the species it does belong to, it will have a true entry. Now we're going to train our layer. So we have 100 neurons and the ReLU activation function, and the output layer is going to have 3. That's because we have 3 categories. And we're going to use the RMS prop, the categorical cross entropy loss function, because this is the one we use for multi-class models. And we have metrics for accuracy. Now we're going to fit it, and we see that we have an accuracy of around 96.7%. Now we're going to try the same thing, except this time we're going to use layers that have 10 neurons instead of 100. So when we fit this and take a look at the accuracy, we can see we only get 63.3%. And that's because with so few neurons, the model is not able to interpret the patterns, leading to a lower accuracy. So how do the number of layers or hidden units affect the accuracy of our model? If it's too low, as you can see above, then it may not be able to detect the pattern, leading to a low accuracy. If it's too high, which we'll see later on, this may lead to overfitting, which could decrease the accuracy. Do we always suffer from overfitting? For a small data set like this, it's very likely to suffer from overfitting as opposed to a larger data set. But this can be mitigated in the part 4. We'll see afterwards. How can we detect overfitting? If there's a disparity between your training accuracy, which is usually a lot lower than your testing accuracy, there is likely to be overfitting. How can we reduce overfitting? So for a larger data set, you may want to increase the number of layers or hidden units, or use an optimizer such as Atom. For a smaller data set like this one, you may want to use a simpler model and a simpler optimizer like RMS prop, as well as use the appropriate number of nodes and layers. So we'll take a look at how these change. So if we take a look at the optimizer, we can see that on using Atom, we actually decrease our accuracy. And that's because the Atom optimizer is more complex than RMS prop, but for simpler data sets, it may lead to overfitting, as it quickly moves down the loss gradient a lot faster than RMS prop. If we change the layer number, so here we went from 2 layers to 4 layers, we can see that the accuracy decreased as well. So that's because the model may be picking up on patterns that aren't actually there, leading to overfitting. If we change the nodes, this is a lot more subtle of a change compared to changing the number of layers. So we can see the model accuracy actually hasn't changed that much. However, if we increase the node to an even larger amount, then we could see overfitting. And we've already seen what happens when we decrease the node to a much smaller amount. As for the epoch number, So here I've decreased the number of epochs from 20 to 10. We can see that the model has less opportunity to readjust its weights. So the loss function is still rather high, and because of that, the model accuracy is lower. And lastly, we have the batch size. So the batch size is equivalent to the step size that the model takes in order to reach the global minimum for the loss function. So here we can see we have a large batch size of 90 compared to our training set of 120. So what you can see here is that even at the end of all the epochs, the loss function is still a lot higher than what it is on the other models. And because of that, it is going to decrease. However, increasing the batch size does improve the computational speed of the model. I'm Akin Zong, and this has been my Comp 3132 Assignment 2.